In section 6.3, our objective is to solve differential equations by separation of variables. Let's recall that a differential equation is an equation that contains a derivative. And if we want to solve the differential equation, we want an equation that does not have a derivative. How do we go backwards from a derivative to not a derivative? What's that called? Antiderivative. So we've done this before. We've solved differential equations because we've taken antiderivatives. Get an antiderivative. What's a synonym for antiderivative? Integral. Ultimately, remember that when you've solved a differential equation, your final answer will not contain a derivative. So like I said, we have done this before. We have seen dy dx equals x squared and asked ourselves to find the antiderivative. Now, we didn't spell it out so much in the steps that we're going to show today because they haven't been as complicated of equations, but we've done this before. We've done this solving differential equations. This is the separation of variables technique. We're going to do it on this simple differential equation. If dy dx equals x squared, I start by separating the x's and the y's. What does that mean, separating? Well, moving them to opposite sides. If y's over here and I have x over here, let's move the dx to the other side. So I don't want to make it confusing by doing it to the problem that I wrote. So I'm going to do it right here. So I'm going to say if I have divided by dx, I'm going to say times dx. That'll get it off of this side. So now I have dy equals x squared dx. That's the first step, separating the variables. Steps in solving a differential equation: 1, separate the variables. Now, in what way? Because we don't want to just add or subtract or multiply or divide, whatever moves it over. We want to move it over in such a way that it's the x stuff times dx, because when we move to the next step of taking the antiderivative of both sides, that's the format where how we usually see the integrals is integral stuff times dx, integral stuff times dy. Now here our invisible stuff is a 1, but it's still stuff times dy. So when I say separate the variables, what I mean is I want stuff that has y in it times dy, stuff that has x in it times dx. Not added to it, but multiplied to it. That's what it means by separating the variables. Then we can do what I'm showing next, which is taking the antiderivative, or more succinctly stated, integrate both sides. Right? It's an equation, so we can do it to both sides. Well, now that I see I'm doing the integral of 1 dy, I know that that's y. On the right side, the integral of x squared is x cubed over 3, and I'm going to put my collective plus a constant on that side. Now you may be asking, why am I not putting it on both sides? I could, but here's what it's going to look like. Y, and maybe I move that over a little bit, y plus a constant, I'm going to call that c sub 1, and x cubed over 3 plus another constant, call it c sub 2. Well, if it's a general constant anyway, we're using a letter for a constant, if I move this constant over to join with that constant, well, what does it make? Another constant. So whether I have a constant here, a constant there, a constant everywhere, or just a constant in one spot, it's still adding a general constant. So I usually wait till the end to add my general plus c. Now, we're only finding general solutions for the first two examples. But if it's needed to find particular solutions, so the third step is conditional. If there is an initial condition, then plug it in to find the C, if there is an initial condition. To build on that, if there is an initial condition and we find the C, then use the C that you found and solve for f of x. Now, you may have to solve for f of x regardless of finding the C or not. We're going to do a variety of examples so you'll be able to get a feel for the different types you'll see. Find the general solution, just the general solution. So that means we are going to have a plus C, or we're going to have some sort of general constant in there. To the following differential equations. Well, where's the derivative in here? Y prime. It's kind of disguised. So my first step in here is rewriting y prime so that it says dy dx. Like this. Then I think I want to separate the variables. What does separate the variables means? Get stuff times dy equals stuff times dx. Well, notice dy dx is subtracted with other things. That is useless. So let's unsubtract it. Let's add it so that it goes away to the other side. There we go. Now I see y's over here and y's over here. I want my y's on the same side. Now, a question that's commonly asked is, how do I know that I want to bring my y's over here and not my x's over here? Because I have more x's over here than I have y's. Well, the answer is simple. Look for the thing that's in the numerator. That's the thing that is supposed to stay over here. The dy, if that's in the numerator, it stays over here. If the dx is in the denominator, it's got to move. So if dx is in the denominator, I'm going to say times dx times dx. What does that leave me with? X dy equals 3y squared dx. Now I'm still mixing up my x's and my y's, and that's no good, but I'm in a better position where I have dy on top, dx on top. Now we're getting somewhere. Let's keep moving stuff. Let's get rid of the x's. Divide by x, divide by x. Send that to the other side. dy equals 3y squared dx over x. We're getting closer, but it's still annoying that we have the y over here when it should be over here. Now, if you feel comfortable doing multiple steps at once, go for it, that's fine. Let's move this y squared over to the other side. So divided by y squared, divided by y squared. What do we have now? dy over y squared equals, I got rid of the y squared on this side, right? There it is, 3 over x dx. Now I could have moved the 3 with it, but a 3 can go on either side. It's not an x, it's not a y, it can go on either side. Now I'm ready to integrate. But am I really? Do I want to integrate with it called dy over y squared, or would I rather integrate with it called y to the negative 2 dy? Now this one, pull the 3 out and see 1 over x dx. Now we can do the antiderivative a little bit easier. I'm going to move up here to show it to you. So we've got y to the negative 1 over negative 1 equals, remember I'm saving my plus c to the end, 3 natural log of the absolute value of x. There's my collective plus c. Now I don't like to leave negative exponents, so I'm going to write negative 1 over y equals 3 natural log of the absolute value of x plus c. This is an equation that has no derivatives. Therefore, this is a general solution. I can say that this is a general solution. Now, I often am asked to find the general solution of y equals f of x, meaning I solve for y. So if it's asked to solve for y to get y equals f of x, then we're going to need to go a little bit further. Well, there's not that much more to do here. Maybe multiply by the negative. So 1 over y equals negative 3 natural log of absolute value of x plus c. Again, my c is just absorbing any of the multiples in there, and then take the reciprocal. So negative 1 over 3 natural log of the absolute value of x plus c. That'll work. So this is another general solution. Both of them very good answers. It just depends on what you are asked specifically to find. Let's try another one. I've moved to where I have a little bit more room to work on this second one. Let's start by separating our variables. So I see dy is on top, therefore I want to get the y over here. So dy over y by dividing by y. I want the dx to move to the other side because it's on the bottom. So I multiply by dx and get dx over x squared. Now I'm ready to integrate. Well, I may want to rewrite this a little bit differently, like this, 1 over y dy, and the integral of x to the negative 2 dx. Antiderivative is natural log of absolute value of y. Save my plus c to the end. Antiderivative is x to the negative 1 over negative 1 plus c. Rewrite this a little bit better. Natural log of absolute value of y equals negative 1 over x plus c. Now, this is a general solution. However, you must know how to solve for y, because a lot of times they will ask you for the solution y equals f of x. So let's go through how to solve this type of equation if they want it y equals f of x. So let's start. Natural log of absolute value of y equals negative 1 over x plus c. How do I make the natural log go away? It's called exponentiating. We exponentiate both sides with base e. Exponentiate both sides of my equation with base e. Why base e? Because of the inverse property. That leaves me with just absolute value of y on the left, e to the negative 1 over x plus c on the right. Now we're going to work with this a little bit because we know our exponent properties say, over here, our exponent properties say that we can change this to e to the negative 1 over x times e to the c, because when I multiply numbers with the same base, I add the exponents. Okay, the left side will stay the same. Now, e is a constant. To another constant really is just a general constant. So I'm going to, instead of write this as e to the c, I am just going to call this c, a general constant. Now, watch what happens when I have to take away the absolute values. Well, I'm going to say plus or minus, I'm going to move this c in the front, ce to the negative 1 over x. Well, what's the difference between positive c or negative c? If I'm just saying it's a general constant, it can absorb those constants that are multiplied to it. Now, there are times that we don't want to just do that, but that comes when we plug in an initial condition. Right now, while that's still a general constant, it can absorb that plus or minus. So ultimately, this is the best general solution. This is another general solution, but a much more simplified one, and one that you must know how to get to. Let's take a look at finding some particular solutions. How do I know I'm asked to find a particular solution? Well, it says find a solution It says y equals f of x, so I have to solve for y, but what tells me it's a particular solution is it has an initial condition. This is the initial condition that'll help me find my c. So let's take our differential equation and let's separate our x's and our y's. dy is on top, so I want to bring all the y stuff to the other side. Multiply by the y stuff, e to the 2y equals multiply by dx, 3x squared dx. Now I can take the antiderivative. Antiderivative of e to the 2y is e to the 2y over 2. If you're not sure how to do that, go back and rewatch 5.4. I'm going to save my plus c for the end, antiderivative of this side, x cubed, and there's my collective plus c. Now at this point, I have a general solution. This has no derivatives in it, so this is a general solution. Now I do want to solve for y, but I also want to know my c because I'm given an initial condition. So the easiest thing for this at this point is step 3, using the initial condition to find the c. So now we're going to use the initial condition. So let's see, what do we have? F of 0 equals 1/2. That means the x is 0, the y is 1/2. So e to the 2 times 1/2 over 2 equals 0 cubed plus c. This makes e to the 1, so that's e over 2. This makes 0, so c equals e over 2. I'm now going to rewrite my general solution, but with the c that's known. E to the 2y over 2 equals x cubed plus e over 2, or 1/2 e, right? I'm using this c, plugging it back in there. There's my c right there. Now I make sure I'm giving the solution the way it's asked. Y equals f of x. So now I need to solve for y. Well, I need this over 2 to go away. So let's multiply both sides by 2. 2x cubed plus e. I multiplied by 2, right? I took this times 2. I took this times 2. Both sides times 2. Now I need to make the y get out of the exponent, so we'll use our inverse property, the natural log. Natural log of e to the 2y equals natural log of 2x cubed plus e. That inverse property helps me to get the exponent that's stuck out of the exponent. 2y equals natural log of 2x cubed plus e. And finally, divide by 2. Y equals 1/2 natural log of 2x cubed plus e. And now I have a solution of the form y equals f of x. And there's no plus c because of the initial condition.